Hello and welcome. Today we'll be talking about the root locus analysis technique, which is one of the prominent ways in which Laplace domain analysis is applied for designing controllers. Let's look at a simple seesaw system. This simple seesaw system, for example, you could have a PI controller, and the PI controller would have a transfer function GC is equal to KC times tau is plus 1 divided by tau is, and then your characteristic equation would be 1 plus GCGP is equal to 0, and so what you will get is 1 plus KC times tau is plus 1 divided by tau is times GP is equal to 0. That's the closed loop characteristic equation, and depending on what GP is, you will essentially get a polynomial of S which is equal to 0, which is your characteristic equation. And in this characteristic equation there will be terms that have the controller tuning parameters Kc and tau I in it. Now the principal controller tuning parameter is Kc. We use rules of thumb for obtaining tau I and tau d. So the real question is, what should Kc be given tau I, and if it's a PID controller, given tau I and tau d. Now as Kc is changed, the coefficients of the closed loop characteristic equation polynomial will change, and as the coefficients of the characteristic polynomial change as Kc is changed, the location of the roots will change, and as the location of the roots changes, the dynamic response of the closed loop system changes. So in short, the roots of the closed loop characteristic equation are a function of Kc. Closed loop characteristic equation roots are a function of Kc. So the root locus is essentially the locus of the closed loop characteristic equation roots as the controller gain magnitude is varied from 0 to infinity. 0 magnitude implies no control, infinity of course implies very aggressive control. So if you look at a closed loop system, it can be decomposed, or what shall we say, it can be put in a block diagram format. That's like this. There's a gain, and this gain is going to get changed. There is a transfer function G, we are looking at this kind of a system. Of course there's a disturbance. Right now we are ignoring that because the disturbance has got no effect on the closed loop characteristic equation, so we can ignore the disturbance for the time being. So we are looking at a system of this kind, and as K is changed, the negative feedback loop gain is changed. How do the closed loop characteristic equation roots move? So the locus of those roots is called the root locus. So if you look at the feedback block diagram on your screen, then the loop transfer function is GCGP, and this would, you can take a gain out, and then you will have a numerator polynomial in S and a denominator polynomial in S, which can be factorized into a bunch of zeros and a bunch of poles. And so you have GCGP is equal to Kg, where G in general is as shown here, and K is a parameter which is the loop gain, which we are going to change, which we are going to adjust. Okay. The closed loop characteristic equation is 1 plus GCGP, which is 1 plus Kg is equal to 0. And what that means is 1 plus k times product of zeros, s minus zeros divided by product of s minus poles must be equal to 0. And what that means is, this guy is g, by the way, without the k. This guy is g. What that means is g should be equal to minus 1 by k. So now we got to think this through a little bit. You see, g is a function of s. S in general is a complex variable. It can be any complex variable. Those special values of S that satisfy the closed loop characteristic equation over here those are the roots of the closed loop characteristic equation. And what this equation implies is we are looking for those special S values for which g turns out to be a negative real number. This is a negative real number. I repeat, we are looking for those special values of S. See, if S is in general a complex number, then g, which is a function of S, is in general a complex number. Now the closed loop characteristic equation requires that g is equal to minus 1 by k, and k should be positive for negative feedback. Therefore, what this means is we are looking for those special S values which, when substituted into g, end up giving us a negative real number. And if we obtain such a negative real number, then that particular candidate S value is on the root locus. Yeah, so that's the idea behind the root locus technique. And it is good to verbalize it. S is a complex number in general. GS is therefore a complex number in general, and therefore this equation implies that we are looking for those special values of S for which g of S is a negative real number. Now let's look at the g plane, and let's look at the S plane. This is the S plane, this is the G plane. Real, imaginary, real, imaginary. If I choose a particular value of S, I will get some value of G, which in general could be anywhere. Let's say it's over here. So this particular value of S does not result in a negative real number. Therefore, this is not on the root locus. If I happen to hit such a value, let us say this is a value of S for which G turns out to be a negative real number, then this particular value of S is on the root locus, lies on the root locus. This is what we mean when we say that we are looking for those special values of S for which G of S is a negative real number. Now when G of S is a negative real number, if you look at G, if it's a negative real number, so let's say this is a negative real number, then in polar form the number G of S would be negative real, so it will have a magnitude times e to the power 180 degrees 3 times 180 degrees 5 times 180 degrees, or minus 180 degrees 3 times minus 180 degrees, and so on and so forth. So what this means is that we are looking for those special values of S which result in a G with an angle of odd multiple of pi. That's the angle condition. Angle of G, because G must be negative real, that means that the angle of G must be an odd multiple of pi plus minus. So plus minus pi, plus minus 3 pi, plus minus 5 pi. So in other words, we are looking for those special values of S for which the angle of G is an odd multiple of pi. This is the angle condition, and by invoking the angle condition, one can make a very neat qualitative sketch of the root locus, and then one can do exact calculations to figure out critical points on that root locus that one is interested in. For example, what is the gain at which the roots are on the dominant roots are purely imaginary, which means you are on the verge of instability. What are the break points? What is the gain at which the root subtends an angle of the dominant root subtends an angle of 60 degrees, which corresponds to a closed loop damping coefficient of I don't know what, yeah, and so on and so forth. So from this angle condition, lots of construction rules can be derived, and those construction rules can be applied to construct the root locus. Okay, we'll go over those construction rules, but it is useful to once again summarize or state what we are trying to do. So we have the S plane and we have the G plane. Where G is equal to product of S minus Zj divided by product of S minus poles, product over J, product over I. So if I take a value of S, I choose some candidate value of S, I get some value of G in general. That's how it would be. I'm looking for those special values of S for which G turns out to be a negative real number. Notice that for real systems, order of the numerator will be usually less than order of the denominator. It certainly cannot be greater than the order of the denominator. So if the order of the numerator is less than the order of the denominator, then one can see that if S becomes large, G goes to 0. For real systems, if S becomes large, G goes to 0. So in other words, what we are looking for are those special values of S for which G moves along the negative real axis. But what are those special values of S for which G lies on the negative real axis? In general, if you use a value of S, G would be a complex number. If S moves along some path in the S plane, G will move along some path in the G plane. We are looking for those special paths on the S plane for which G moves along the negative real axis. Okay, so now that we understand this, let's go through some construction rules. So remember, we have G equal to and I goes from 1 to n and j goes from 1 to m. M is less than or equal to n. So if you look at the closed loop characteristic equation, which is 1 plus kg equal to 0, it will be a polynomial in S, and that polynomial is of order n. Because it is of order n implies there are n roots of the closed loop characteristic equation. Because there are n roots, that means, and each of these n roots will move as k is changed. Each of these n roots will move as k is changed. So that means there are n root locus branches. So the root locus has n branches. Now the root locus starts at magnitude of k equal to 0 and it ends at magnitude of k going to infinity. Now you can see the closed loop characteristic equation is, so if k goes to 0, g must go to minus infinity, and g will go to minus infinity when s is equal to p. It can also be looked at in a much simpler way. I can say that g is equal to a numerator polynomial in s divided by a denominator polynomial in s, and therefore 1 plus kg is going to be denominator polynomial plus k times numerator polynomial equal 0. This is the characteristic equation. And when k goes to 0, you can see that the roots of the denominator polynomial are the roots of the closed loop characteristic equation. Roots of the denominator polynomial are the poles of g. So what this means is that the root locus begins at the poles of g, at the open loop poles, open loop transfer function poles. So the loci begin at the n open loop poles. When k goes to infinity, g must go to 0. If g goes to 0, g goes to 0 when s is equal to zj, or if m is less than n. So there are n branches. Of these n branches, m branches end at zeros, because at a 0 g goes to 0 and k going to infinity implies g must be going to 0. Yeah, k going to infinity implies g must be going to 0. So there are n branches. Of those n branches, m end up at the open loop transfer function zeros, at open loop zeros. What about the remaining n minus m branches? What happens to the remaining n minus m branches? Well, if m is less than n, let us say n is 5 and m is 2, then there are 3 branches. Which way will they go? Well, they end up in asymptotes, and you can see that if m is less than n, then as magnitude of s tends to infinity, magnitude of g tends to 0, because g then is approximately 1 by s to the power n minus m, and n minus m is greater than 0, and this will tend to 0 for magnitude of s tending to infinity. And the locus requires, the condition for a candidate s point to lie on the locus is that as k tends to infinity, g must go to 0. So g goes to 0 when s is equal to zj, or it will go to 0 for asymptotes. That means s is very large, magnitude of s is very large, for those special asymptotes that satisfy the Engel condition. So there will be n minus m asymptotes. Asymptotes meaning large magnitude S. Now if you look at the S plane, everything in that infinite very large radius circle has large magnitude S, but we will be getting only those special values of S which are large that satisfy the angle condition that will be on the root locus. But for the time being, the rule is the loci begin at the n open loop poles, they end at the n open loop zeros, and n minus m asymptotes. And the last thing that I wanted to tell you on this slide was that the root locus is symmetric about the real axis. It is symmetric about the real axis because, why is it symmetric about the real axis? It is symmetric about the real axis because the coefficients of n and d, the polynomials in S, are all real, and you can get real polynomials if and only if the factors occur in complex conjugate pairs. And because the factors or roots occur in complex conjugate pairs, the root locus will have to be symmetric about the real axis. So root locus is symmetric about the real axis because roots occur in conjugate pairs. Okay, now let's talk about asymptotes. Oh, locus on the real axis. Okay, consider a situation you just do the pole zero map of the G transfer function. So the poles and zeros of G, just plot them on the complex plane. I'm just taking some example. Blah 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 blah. Maybe put a zero somewhere. यहाँ पर एक zero बना देते हैं, चलो. So the crosses are poles and the circles are zeros. Okay. All right. So now the question is, does locus exist on this part of the real axis? On this part of the real axis. That's the question that I'm asking. So say, okay, let's take a candidate point over here. I take a candidate point. Angle subtended by the pole, by any real pole is 0 degrees. This guy is also subtending 0 degrees because this guy is also subtending 0 degrees, or you could say minus 0 degrees because poles occur in the denominator. And the 0 is subtending an angle of plus 0 degrees. So all of these poles and zeros are subtending 0, 360, 2 times 360, so 2 pi, 4 pi, 6 pi, that's these kinds of angles. And the angle of G is going to be equal to sum of angle of S minus ZJs minus sum of angle of S minus PIs. Yeah, summed over J, summed over I. And my candidate S was over here, so angle of S minus ZJ is 0, angle of S minus P is also 0, all the poles are right. So clearly for any point on this side, the angle of G is 0, which is not an odd multiple of pi. Therefore locus does not exist on this part of the, locus does not exist here. Okay, fine. Let's look at a candidate point over here. we see that all the poles to the left, the real poles and zeros to the left, subtend no angle. If you look at the complex conjugate pairs, how much does this subtend? S minus, this is minus phi because anti-clockwise, and this guy is plus phi. When you add these two up, they will cancel each other, so the net angle subtended even by the complex conjugate pair is 0. And this guy subtends an angle that is pi. So in this case, the angle subtended on any point between this pole and this pole is going to be, for any S candidate, the angle is going to be pi, which is an odd multiple of pi. Therefore, all the points between this pole and that pole, between these two poles, are on the locus. So this is part of the locus. Let's look at candidate points over here. In this case, again, the complex poles will subtend an angle 0. The poles to the left, poles and zeros to the left, if I look at a point over here, the poles and zeros to the left, that is this guy and that guy, they will subtend an angle 0. The poles to the right on the real axis will subtend an angle pi each. So this guy will be pi, that guy will be pi, so minus pi plus minus pi, minus 2 pi. That's an even multiple of pi. Therefore, locus does not exist on any point between this and that. Let's look at this guy. This pole will subtend an angle minus pi, this pole will subtend an angle minus pi, this pole will subtend an angle minus pi, so minus pi plus minus pi plus minus pi is minus 3 pi. The 0 will subtend an angle over here of 0 degrees. The complex conjugate pair will subtend a net angle of 0. So therefore, any point between the 0 and the pole, between this and that, any point on the real axis over here satisfies the angle condition, because the angle is an odd multiple of pi, odd multiple because 1, 2, 3, 3 pi or minus 3 pi. So therefore, this part is also on the real axis. So the rule comes out that locus exists on the real axis if number of poles and zeros to the right is odd. Locus does not exist on real axis if number of poles and zeros to the right is even. So in this example over here, what I mean is over here in this section, number of poles and zeros to the right is 0. That's not an odd number, so locus does not exist in this part. Over here, number of critical points, that means poles and zeros, open loop poles and zeros, to the right is 1, which is odd, therefore locus exists here. Over here, number of points to the right are even, and therefore locus does not exist. And over here, number of critical points to the right is odd again, so locus exists. And if you come over here, number of critical points is 1, 2, 3, 4, that's even, so locus does not exist on this part. Okay, so locus exists on real axis if the number of critical points being open loop transfer function poles and zeros, so number of critical points to the right are odd. Okay, now let's talk about asymptotes. The angle of the asymptote, so now is given by an expression over there. I thought that I'll try and derive it. So we have G is equal to product of S minus Zj product over J divided by product over I of S minus Pi, and this guy will turn out to be a polynomial s to the power m minus minus summation zj time s to the power m minus 1 plus other terms, and s to the power n minus summation pi s to the power n minus 1 plus lower order terms. Now for asymptotes, magnitude of s is large. If magnitude of s is large, I can approximate g as by ignoring all smaller order, by only retaining the highest order terms in the numerator and the denominator respectively. So what I will get is approximately equal to 1 over s to the power n minus m. Yeah, that's what g is. And we know that g should be equal to a negative real number, or you can also say 1 by g should be minus k. And if you look at 1 by g, what that means is s to the power n minus m should be equal to k, or negative k. What that means is g is not g, 1 by g is approximately equal to this. So now what this means is, if those special values of s that satisfy the angle condition that lie on the asymptote, this is the equation, approximate equation of that asymptote. And for this equation, what we have is, because the right hand side is a negative real number, angle of s to the power n minus m must be equal to plus minus 2k plus 1, must be an odd multiple of pi. Therefore, angle of s, the candidate s that lies on the asymptote, must be equal to plus minus into pi divided by n minus m. That is the angle condition. Now rule 7 gives us the real axis intercept of the asymptote. You know, let's say the angle of the, okay, before I do that, let's go back. By the way, this gives us, if n minus m is 1, there's one asymptote and angle is 180 degrees. So that's the asymptote, 180 degrees. If n minus m is 2, the asymptotes occur at plus minus pi divided by 2. So that's plus minus pi by 2. So the asymptotes are, this is for asymptotes for n equal to 1, or sorry, n minus m is equal to 1. For n minus m is equal to 2, there are two asymptotes, one going up like this, plus pi by 2, the other one going down like this, minus pi by 2. For n minus m is equal to 3, there are three asymptotes, plus minus pi by 3 and pi. So 60 degrees, minus 60 degrees and pi. So that for n minus m is equal to 3, the asymptotes, and right now I'm showing all the asymptotes as passing through the origin, but these could be shifted also and they would still be satisfying the angle condition. So there are actually infinite such candidates. The next rule, what is the real intercept of this real axis intercept of these asymptotes, that will exactly locate the asymptotes. Similarly, n is equal to 4, what will you get? You will get whatever you will get. For 5 you will get what, 36 plus minus 36, 108, and things like that, you know. So this is n minus m is equal to 3. Okay. Now, so let us say there are 3 asymptotes. Let's say there are 3 asymptotes, and one of them is at an angle of 60 degrees. Okay, so this is angle 60 degree, this is also angle 60 degree, this is also angle 60 degree, this is also angle 60 degree. Which one is the asymptote? Now in order to fix the asymptotes, the rule 7 gives us the real axis intercept sigma of the asymptotes, and the rule is written here. Let's try and derive it. How to derive it? In this case we will again take G is equal to product of S minus Zj divided by product of S minus Pi, which turns out to be S to the power m minus summation of Zj into S to the power m minus 1 plus other terms divided by S to the power n minus summation Pi S to the power n minus 1 plus other terms, lower order terms. Okay. We'll say that we'll approximate G for large S using the first 2 terms in the numerator and the denominator respectively. So and the characteristic equation requires that G should be equal to minus 1 by k, or 1 by G should be equal to minus k. We'll take 1 by G, and so what that means is S to the power n minus summation Pi into S to the power n minus 1 divided by S to the power m minus summation Zj times S to the power m minus 1 should be equal to minus k. Now let's just do the division. If you do the division, what will we get? We will get S to the power n minus m minus summation Pi minus summation Zj to the power S to the power n minus m minus 1 plus higher order term or lower order terms, and I will say I will ignore them, and so what I get approximately is S to the power n minus m minus summation pi minus summation zj to the power into s to the power n minus m minus 1 is equal to minus k. That's what we get approximately. And I do another approximation. This guy in the left hand side is approximately equal to s minus summation pi minus summation zj divided by n minus m to the power n minus m. This should be equal to minus k, a negative real number. Now if you look at this guy, if you do the binomial expansion, what will you get? S to the power n minus 1 plus n minus m times this multiplied by s to the power hang on. Okay, if you do the binomial expansion of this guy, this will be s to the first term will be s to the power n minus m. Second term would be n minus m multiplied by s to the power n minus m multiplied by this guy, which is minus pi minus. So when you multiply these guys, these two terms get recovered. There will be n minus m minus 2 term, n minus m minus 3 terms, but we are anyway ignoring them, and we are saying that we are only going to retain the two highest powers of s. So in that sense, this approximation makes sense, and therefore what we get from here is s minus sigma to the power n minus m is equal to minus k. If I shift my origin to sigma, if I say s minus sigma is equal to s1, then what I get is s1 to the power n minus m is equal to minus k. And in the s1 plane, the asymptotes are passing through the origin. In the s plane, the asymptotes are passing through s equal to sigma, and therefore sigma is equal to summation pi minus summation zj divided by n minus m is the real axis intercept of the asymptotes. All right. Usually what happens is, so let's say does locus exist here? No. Does locus exist here? Yes, because the number of poles to the right is odd. So locus exists here. What that means is the locus starts moving this way, and from this pole, as kc is increased, locus starts moving that way. You can see that after at some particular value of kc, you will get two repeated roots. And now if you increase kc again, you see you will get a breakout from the real axis. So where does this breakout point exist? Similarly, you could also have break-in points. So for example, let us say you got let's see, okay, and let's say it's like this. And if I look at this guy, number of points to the right Oh man, we'll have to think about this. Okay. If I look at this guy, locus exists on this part because number of critical points to the right is. Locus also exists on this part because critical points to the right is odd. So obviously there is going to be a breakout. Once there is a breakout, we know that the loci end at 0. So one of the branches will end at this 0. The other branch will end up in the asymptote. So clearly the root locus will be qualitatively of this kind. Mirror image around the x-axis, along the real axis. This is a break-in point. This is a breakout point. Here is a break-in. And here is a breakout. The locus breaks out into the complex plane and breaks into the real axis from the complex plane. So breakout and break-in points exist many times in root loci. Now, at the break-in or breakout point, the closed loop characteristic equation has repeated real roots. And you know, if there are repeated roots, so let us say there is a polynomial in S which has many roots. Which has many roots. Oh boy. There is some translation happening. इसको escape कराओ यार, ये कैसे करेंगे? Skip. I don't know what the hell is going on. Anyway, I'll continue. Okay. I don't like Alexa or Siri or Cortana. I like to be in charge. What the hell was I saying? So if let us say there are PS has got repeated roots. If it's got repeated roots, so let's say S plus A, S plus B, and let's say S plus C is repeated twice. You will see that if I take the derivative of the polynomial at S equal to the repeated root, repeated root is minus C actually here. If I take the derivative at the repeated root, this derivative will turn out to be 0. Because S plus C whole square derivative will be 2 times S plus C. When you put S equal to minus C, that term will go to 0. The other two terms will anyway have S plus C whole square. So when you put S equal to minus C, again those two terms go to 0. So the derivative of P of S at S equal to minus C at the repeated root. So at a root, at a distinct root, the polynomial goes to 0. At a root that is repeated twice, the polynomial goes to 0, derivative of the polynomial also goes to 0. If the derivative of the polynomial is going to 0, what is that supposed to mean? It is supposed to mean that, by the way, what is the polynomial? 1 plus kg. That's the polynomial that we are talking about, right? If this polynomial has got repeated roots, then at that repeated root, d by ds of 1 plus kg must be equal to 0. If d by ds of 1 plus kg is equal to 0, then k times d by ds of g must be equal to 0. That means dg by ds must be equal to 0. That means magnitude of g shows a maximum or a minimum depending on whether it's a breakout point or a break-in point. It turns out for a breakout point, magnitude of g shows a maximum. For a break-in point, magnitude of g shows a minimum. So what you do is you just plot the gs. So for example, let us say I've got 3 poles. and I want to calculate where is the, so locus will exist over here. Where is the breakout? If I want to, and of course locus will, that's the asymptote. N minus m is 3, so you'll get 60-degree asymptotes. You can calculate. So basically the break, the qualitative shape of the root locus in this case is going to be like this, and these are 60-degree and minus 60-degree lines. So you got the 3 asymptotes. Question is, where does this break in occur? What you do is you plot G, magnitude of G versus S, wherever the magnitude is maximum. In this case, because it's a third order system, you differentiate a third order system, power of S will reduce by 1, you'll get a quadratic. You can get quadratic roots. There will be 2 roots. One of those roots will lie in this range. That's the root that we are looking for. That gives us the break-in point. But if the order of G is much larger, then the only way is to plot G and look for the maximum, and wherever that maximum is, that corresponds to the break-in point. Similarly for breakout point, break-in and breakout. Okay. Angle of departure from a complex pole. Well, again, let's just do a simple example. Let's say I've got this and I've got 2 complex poles. Obviously locus exists on this part, so that's one asymptote. Third order system, so you'll have what will be the real axis asymptote will be this plus real part of this plus real part of this divided by 3. So it will be somewhere over here. Let us, you do that calculation. Let's say it turns out to be over here. So obviously your asymptote is going to be like this. Now from this point the locus departs and it will hit the asymptote, this asymptote, and from this point the locus will depart and hit that asymptote. Now the question is, does it depart like this and hit like that, or does it depart like this and hit like that? And obviously this would be the mirror image. So there is the angle of departure. So this would be the angle of departure of the locus from a complex pole. How do we get this angle of departure? Let me erase some stuff here. How will we get it? We'll get it by invoking the angle condition in the vicinity of the complex pole. So let us take a point that is on the locus but it is very close to S, which is very close to the pole. Then the angle that guy is subtending is, let us say, phi. Then since this point is very close, the total angle subtended is phi plus or minus as you please. So the total, oh hang on, so the angle would be phi, sorry, let's in, oh boy, what have I done? What have I done? Okay. So the angle of this pole is minus phi. Angle from this pole is this guy, that's minus pi plus whatever this guy is, let's call this phi 1. Angle from this pole is plus pi by 2, and therefore this should be equal to odd multiple of pi, so I can take plus pi or minus pi. Let's say I take plus pi, and so what I get is this need not be there. I can just say plus phi 1, and so the angle subtended, and let's just take minus pi here because plus minus convenience. So pi well let me put it differently. Let's put some numbers in here. So let us say this is minus 1, and let us say this is minus 2, and let us say this is 1 and this is minus 1. So the two complex poles are minus 2 plus minus j, and minus 1 is the other pole. So invoking the angle condition would be as follows. Angle subtended by this guy is how much? This would be tan inverse kitna? Tan inverse 1 by 1, and this is the angle, and I need to have this angle is actually negative, but since it's a pole occurs in the denominator, so the angle would become positive. Okay, what about the angle of this guy? This angle I don't know, so I will say that that angle is minus phi because it's a pole. What about the angle of this guy? The angle of this guy is pi by 2, but because it's a pole it will be minus pi by 2, and this should be an odd multiple of pi. So we'll just take it as pi, and therefore what happens is phi must be equal to minus pi plus tan inverse 1 is pi by 4 minus pi by 2. So this guy turns out to be minus pi by 4. That means the locus from will leave at an angle of minus pi by 4. Minus pi by 4 means minus 45. So it will go like this, and then of course it will depart at an angle of minus 45, and then of course it will hit the asymptote. So I hope it is clear. So and you can see this is how the angle condition gets invoked. So you just have to invoke the angle condition by properly accounting for the complex angles. Okay. The other thing that I wanted to say was angle of arrival at a complex 0 again comes from the angle condition. Okay, so there is a very nice iterative procedure for calculating for calculating the break-in or breakout points. And you see, let's consider a very let's consider I'll do the illustration, and then that should hopefully clarify things for you. So let's say GP is equal to 1 over s plus 1 into 2s plus 1 into 4s plus 1 into 1.6 s square plus 2.4 s plus 1. And if you take the quadratic roots of this guy, you will find that, so the roots of the open loop poles are s equal to minus 1, s equal to minus half, s equal to minus 1 by 4, and if you take out the roots of this quadratic, it will turn out to be minus 3 by 4 plus minus 1 by 4j. So it's a fifth order system. There's going to be 5 asymptotes. Now if I plot my root locus approximately very quickly, so this minus 1 by 4, this is minus half, this is minus 1, and this is minus 3 by 4. Okay, and these are my two complex poles. Obviously root locus exists here, and so there's going to be a breakout point. Question is, where is that breakout point going to be? So what we do is we take, so let me just zoom into this area. So there's two poles here, and I'm looking for a breakout point. So let's say breakout point is someplace here, and then I break out and move up a little bit, and this is highly magnified, so this little bit infinitesimal movement up is delta. Now at the breakout point, the angle condition is satisfied. So the sum of angles subtended by all the poles and zeros of the open loop transfer function is an odd multiple of pi. So the angle condition is satisfied. Now if I move up, break out, then how much does the angle change that which is subtended by the other poles? So for example, here the angle will change by this much. This guy, the angle will change by this much, but a negative sign. Yeah, and if there is a complex pole which is shown here, then the angle will change. You know, look at this guy, the complex pole over here, this chap, complex pole over here. I break out. If I break out by delta, then the angle because of P2 changes by delta phi 2, angle because of P1 changes by delta phi 1, and you can actually derive this by using symmetry of angles. So what is the area of triangles? So if you look at this triangle, this small triangle, if you look at this triangle, its area is half times base times height, and height is b. This is also equal to product of the two sides, half times product of the two sides times sine of the angle included between the two sides. What is the magnitude of the two sides? It's square root a square plus b square into square root minus delta whole square plus b square sine delta phi 1. And for small deltas, delta phi 1 will be small, therefore sine delta phi 1 is equal to delta phi 1. Okay. For the other triangle, this chap will have half delta b is equal to half times square root a square plus b square times square root a plus delta whole square plus b square times sine of delta phi 2. And this goes to delta phi 1 for small delta, and this goes to delta phi 2 for small delta, and therefore the change in the angle contributed by P1 and P2 is going to be you see, this guy is subtending this angle which is negative. Later on it is subtending this angle, so the angle contributed by P1 has actually increased. Similarly, the angle contributed by P2 has also increased. So what this means is, if the breakpoint is to the right of the complex poles, the contribution of the complex poles to the angle will be positive. Okay, so change in angle delta phi is equal to delta phi 1 plus delta phi 2. This chap is going to be half to काट ही दो, is going to just add it up, 2 delta b 2 times delta b divided by, in the limit delta is going to the delta square, can ignore, so it's going to be a square plus b square. If you have real poles, what do they contribute? If you have real poles, so like I was saying, so let's say I've got a pole here and I got a pole here and I got a pole here, and breakpoint is to be calculated over here. I break out delta, angle contribution by this pole has increased by, actually if delta is small, tan theta is equal to sine theta is equal to theta. Then we will say that okay, the contribution, this change in angle is going to be delta by whatever this is, delta by, I will call this, I don't know, base b from pole 1. So, and this contribution is positive because it's going anti-clockwise. Over here the contribution is going to be minus delta by, let's call this b2, delta by b2, and the contribution of this chap is going to be plus delta by b3. And because the location of the poles is known, therefore b1, b2, b3 are known, except that there's only one variable, one unknown, which is the distance of the breakpoint from P1. And because the angle condition must be satisfied even in the vicinity, the contribution of the angles by these poles must sum to 0. And from this you get one equation in one variable which can be iteratively solved to get the exact location of the breakpoint. And I think what I'll do is I'll try and show this for maybe it's easier to just delete, erase everything and start afresh. So erase everything and start afresh. Okay, so we have Gp is equal to 1 over s plus 1 into 2s plus 1 into 3s plus 1, 4s plus 1. What the hell was it? 4s plus 1 into 4s plus 1 into 1.6 s square plus 2.4s plus 1. And if you look at the open loop poles, the open loop poles are s equal to minus 1, minus half, minus 1 by 4, and minus 3 by 4 plus minus 1 by 4j. These are the poles. If these are the poles, then obviously minus 1 by 4, minus half, minus 1, minus 3 by 4, 1 by 4. These are the poles. 5 poles. Want the breakpoint over here. For this breakpoint, let me call these poles 1, 2, 3, 3 prime, and 4. So the angle subtended at the breakpoint by pole number 1. So let us say this distance is A. Then angle subtended, change in angle as I break out due to pole 1 is going to be delta negative delta divided by this distance is 1 by 4 minus A. 1 by 4 minus A. Okay. Due to pole 2, the contribution is going to be delta divided by A. Due to pole 4, the contribution is going to be delta divided by this distance is half plus A. And due to the complex poles, the contribution is going to be 2 times delta times B, and B is this distance. Yeah, B is this distance, and that's going to be 3 by 4 to half plus 1 by 4 plus A. ये क्या हुआ भाई? 1 by 4 plus A whole square plus this distance is 1 by 4 plus 1 by 4 square. This whole thing should be equal to 0. And the delta cancels out. No. 2 delta into B. Where is B? 2 delta into B, and B is 1 by 4 plus A. So the delta cancels out, and what I then get is 1 by A plus 1 over half plus A plus half plus 2A divided by 1 by 16 plus 1 by 16 is 1 by 8 plus half into 2 is half A plus A square minus 1 by 4 minus A is equal to 0. So this is one equation in A. It can be solved iteratively to obtain the value of A. You can, for example, use very conveniently F0 in MATLAB, And if you do it for this example, it turns out that A is equal to 0.1612. And what that means is this is minus 5. So S is equal to minus 0.5 plus 0.1612, that is equal to, that implies S equal to minus 0.3388 is the root that is repeated twice. Break in and break out correspond to repeated real roots, so this is repeated twice. What is the gain at this breakout point? That can be calculated from very simply one plus Kc Gp is equal to 0. Therefore, Kc is equal to minus 1 by Gp. Gp is known, substitute S equal to minus 0.3388 in that and get the value of Kc. Kc turns out to be so break in and break out can be calculated in this manner. Law of conservation of roots, that's actually, see, we have 1 plus k times g, and g is a numerator polynomial in S divided by a denominator polynomial in S. That's your closed loop characteristic equation. Now let us say numerator order is m and denominator order is n, and n minus m is greater than or equal to 2, then what we will get is s to the power n minus summation pi into s to the power n minus 1 plus lower order terms plus k times s to the power m minus summation zeros into s to the power m minus 1 plus lower order terms should be equal to 0. This is what my, now the closed loop characteristic equation, it has got n roots, and let us say those roots are denoted by Ri, and let us say the closed loop characteristic equation factorizes as the closed loop, these turn out to be the factors. Then this will open up as s to the power n minus summation Ri into s to the power n minus 1 plus lower order terms. And if m is less than n by 2 or more, that means if n is, let us say, 10, then s is 8, then m is 8. So the highest power of s would be s to the power 10, next highest power will be s to the power 9, and then you'll get s to the power 8, and here also you'll get s to the power 8, and mixing will happen only in the s to the power 8 and lower coefficient. No mixing will happen here because there is no s to the power 9 term inside the k bracket. There is no s to the power. The highest power here is less than n minus 1. Because it is less than n minus 1, the coefficient of s to the power n remains 1. The coefficient of s to the power n minus 1 remains summation pi. Coefficient of s to the power n minus 2, because m, let us say, is n minus 2, then there will be some mixing. But this coefficient remains untouched, and therefore, because these two are characteristic equations of the same system, therefore summation Ri must be equal to summation Pi, which is the law of conservation of roots. The roots of the closed loop characteristic equation, their sum, and the sum of the roots of the open loop poles, which is this guy, they will be equal if n minus m is greater than or equal to 2. This is the law of conservation of roots. With this, we come to an end of the rules that will help us construct root loci. Let me summarize. Locus has n branches because the characteristic equation has the same order as the denominator of G. If the order of denominator of G is n, closed loop characteristic equation will have n roots. These n roots begin at the poles of G, at the open loop poles, end at the open loop zeros and n minus m asymptotes. The root locus is symmetric about the real axis because the roots occur in complex conjugate pairs, so the symmetry has to be there. Locus exists on real axis only if number of poles and zeros to right is odd. Angle of the asymptotes, there are n minus m asymptotes, so the angle of the asymptotes is odd multiple of pi divided by n minus m. Real axis intercept of the asymptotes is sum of the poles minus sum of the zeros divided by n minus m. The breakout and break-in points can be obtained by maximizing g of s. You could also invoke the angle condition in the vicinity of the break-in or breakout point, and that will give you an equation, a nonlinear equation in one variable, which is the distance of the breakout point from one of the poles, one of the nearer poles. And that distance can then be iteratively calculated by solving that nonlinear equation. Angle of departure or arrival at a complex pole or zero, there should be a pole here. It can be obtained by invoking the angle condition. Angle condition in the vicinity of breakout and break-in point allows iterative calculation of the breakout or break-in point. If n minus m is greater than or equal to 2, then the sum of the closed loop characteristic equation roots is equal to the sum of the open loop poles. These are some of the rules. In the next class, we'll apply these rules to qualitatively sketch some root loci for some example systems. That's what we are going to do in the next class. For now, the class is over. Thank you for your kind attention. Hope you enjoyed the class. See you next time. Thank you and goodbye. It was a long class.